When a suspension bridge carries heavy traffic, the massive steel cables flex and stretch to distribute that weight. Before a single piece of steel is hung, engineers have to map exactly how that tension flows through every single segment. This diagram represents an unsymmetrical cable. We're dealing with uneven support heights, downward point loads of 9 and 20 kilonewtons, and an unknown dip height labeled here as H. Over the next 6 minutes, we are going to solve this entire system. We will calculate the exact tension in every segment, find the absolute extremes of stress, and determine the true physical length of the cable needed. Take a moment to grab your calculator and ensure your trigonometric functions are set to degrees before we proceed. Converting these loads into precise mathematical values allows us to move from a theoretical sketch to a physical design capable of supporting real-world stress. Our first step is achieving global equilibrium. We isolate the entire cable system by removing the physical supports at A and D, replacing them with tension force vectors to create a free body diagram. We start by setting the sum of moments around point A to 0. This requires us to balance the clockwise rotation of the 2 point loads against the counterclockwise pull coming from the support at point D. We take the 9 kilonewton load at 4 meters and the 20 kilonewton load at 9 meters, then set them against the tension of segment CD, which acts at a horizontal distance of 12 meters and a vertical distance of 2 meters. Solving that moment balance reveals TCD is exactly 20 kilonewtons. Now we establish the remaining global equilibrium boundaries by writing out the sum of forces for both the horizontal x-axis and the vertical y-axis. While these two equations currently have too many unknowns to solve, they provide the necessary framework we need before we can analyze the internal segments. To find those internal values, we use the method of sections. We virtually dismember the cable to analyze the forces acting specifically on member ABC. We substitute our known 20 kilonewton value for segment CD into our global equations. This simplifies our math down to 2 expressions. TAB cosine theta 1 equals 12, and TAB sine theta 1 equals 13. Using the identity that sine divided by cosine equals tangent, we can divide these expressions to find our missing angle, 47.29 degrees. With the angle known, we can solve for TAB, which gives us 17.692 kilonewtons. We can now determine the unknown dip height, H. Multiplying the 4-meter horizontal distance by the tangent of our new angle reveals a vertical drop of 4.333 meters. Our final unknown tension, segment BC, is found by summing the vertical forces at joint B. This final calculation yields 12.646 kilonewtons. Dismembering the structure allowed us to expose those internal unknowns, effectively turning a complex system into a series of solvable trigonometric ratios. With all segment tensions solved, we can now evaluate the list to identify the stress extremes across the entire system. The highest stress occurs at segment CD, our maximum tension of 20 kilonewtons. The lowest stress is found in the middle segment, giving us a minimum tension of 12.646 kilonewtons. To find the physical length of the cable, we visualize the 3 segments as the hypotenuses of 3 independent right-angle triangles. By applying the Pythagorean theorem to each triangle, using our known horizontal and vertical distances, we calculate the exact length of each individual cable segment. Combining those 3 lengths gives us the final true length of the cable, 16.165 meters. These peak stress values and geometric lengths provide the exact data needed to specify material thickness and procure the correct amount of cable for construction. Our final blueprint is now complete. Every dimension, angle, and tension limit is clearly defined, leaving no unknown variables in the system. This process is repeatable for any determinate structure. Global equilibrium anchors the external environment, while the method of sections decodes the internal forces. To test these principles, try recalculating this system with a 15 kilonewton load at point B instead of 9. You'll see how the locations of maximum tension shift across the structure. The systematic application of basic equilibrium and geometry reveals the mathematical truth of the system. Each step builds the evidence needed to design structures that are both efficient and secure.